First have 10 minutes, and there will be a QA session in the end. So let's welcome the first presenter, Groundless Truth, a causal framework for proxy labels in human algorithm decision making.
Okay. Hi, everybody. My name is Luke, and today I'm excited to present joint work with Amanda Costin, Stephen Wu, and Ken Holstein titled Groundless Truth, a causal framework for proxy labels in human algorithm decision-making. Predictive models deployed in real-world decision-making contexts often target labels that imperfectly reflect the goals of human decision makers. For instance, the toxicity labels targeted by content moderation models reflect the subjective and context-dependent opinion of the person who annotated an example as toxic or non-toxic. Additionally, models used to support social workers in child welfare maltreatment screening often predict the risk that a child will be removed from their home within 2 years. Yet social workers themselves have reported that this differs from their own goals of assessing immediate threats to child safety. And finally, as we learned about in the wonderful keynote yesterday by Zayed, one widely deployed algorithm that was deployed throughout the United States targeted cost of care as a proxy for medical need. But cost of care is an imperfect proxy because many patients may have historically had lower costs than artificially low costs due to lack of health care insurance or other discriminatory factors. And these examples present a key challenge because models targeting imperfect labels can introduce really damaging downstream impacts. For example, the case that I just discussed by Obermeyer et al., this clinical decision support tool was deployed throughout the country and resulted in 28% fewer Black patients receiving the additional resources that they needed as compared to similarly sick white patients. And this example, along with the many others which we cite in our work, underscore that if a predictive model is targeting the wrong outcome, it's unlikely to help a human decision maker make the right decision. However, when we look at human AI decision-making research, on the other hand, we often see that it assumes that models target so-called ground truth labels. For instance, one body of research conducts experimental human subject studies examining how behavioral interventions such as explanations influence human trust and reliance patterns. And for a good overview of this work, I invite you to check out some work published here at FACT in the session on Monday. Additionally, an additional body of work evaluates modeling techniques that are designed to account for some of the limitations of human judgment. However, really critically, both lines of literature tend to operationalize good decision-making as high accuracy evaluated with respect to proxy labels. But because proxy labels can be an imperfect reflection of human decision-makers' actual goals, accuracy with respect to proxy labels is a really imperfect measure of decision quality. So therefore, in this work, we develop a new framework that helps the FACT community bridge this gap between complexities encountered in real-world model deployments and actual current research practices that are happening on the ground. In particular, we develop a causal framework in which we examine the data generating process that gives rise to predictive model training data sets in detail and examine this connection with proxy validity-related challenges. We show how this framework can help the FACT community disentangle sources of statistical bias impacting proxy labels, better articulate proxy label modeling assumptions, and we re-examine the design of prior experimental human subject studies, leveraging our causal diagram as a background. To develop our causal diagram, we reviewed a diverse set of real-world case studies, synthesized these into candidate diagrams, and stress-tested these by attempting to identify counterexamples. We then reviewed a broad set of relevant literature and worked with different researchers with different domain-specific expertise to verify the validity of this diagram. And so now I'm going to introduce you to our causal diagram with the specific context of predicting heart attack diagnosis. But this actually generalizes to a lot of different algorithmic decision support settings and the employment domains, healthcare domains, lending, as well as many others that we might be familiar with here. In this setting, we have a physician whose decision is being informed by an algorithm, such as which medicine to prescribe. And we also have access here to a model prediction. The goal here is to predict some downstream outcome, such as biological heart attack, based on some joint decision between the model and the human. In this case, there's actually a difference between biological heart attack, whether this occurs physiologically, and the recorded heart attack that we have available in medical records. And in fact, upwards of 45% of heart attacks can be misdiagnosed. They're so-called silent heart attacks. So these two can diverge quite substantially. But we can think about the relationship between these two and formalize it via a measurement error model. Additionally, in these algorithmic decision support settings, we often have access to some administrative records that are used as model features, as well as some human-only features that are only available to physicians, such as the real-time results of electrocardiograms. Given these different information sources, we can then think about how they are related. For instance, model features can impact both the model prediction and the human decision, while human-only features here would only impact the human decision. And we can extend this thought process to fill out the different edges connecting this diagram. But one really important application of this is that we can use it to begin to think really carefully about the different sources of statistical bias that impact proxy labels in model development datasets. For instance, outcome measurement error, which occurs when the label that's recorded in available data differs from the broader construct of interest to human decision makers, such as creditworthiness, recidivism risk, student learning outcomes, et cetera, as one really commonly discussed challenge that arises in this setting. But when we look at this causal diagram more carefully, we can also surface a lot of other more nuanced and complex challenges that can impact proxy labels. For instance, treatment effects occur when prior decisions have some influence on the downstream outcomes, and these occur when you have treatment effects or selective labels, and these have been widely discussed in a lot of different settings, such as child welfare hotline screening, medical settings, et cetera. Additionally, I won't talk about these in detail, but there's additional nuanced challenges such as confounding and selection bias that can actually also impact labels through more indirect paths in our diagram. But an additional really important benefit of this framework is that it can help us as researchers to think about how different algorithmic decision support tasks are likely to be impacted by different forms of this statistical bias that are impacting proxies. For example, in these settings when the human decisions impact downstream outcomes, the full set of challenges that I've just told you about are salient, and there's the things that we need to worry about. And this is the common setting in a lot of real-world algorithmic deployments, such as lending and criminal justice. However, when these decisions do not impact outcomes, only outcome measurement error is of a concern. And this is really important because a lot of these online studies are using these artificial tasks such as nutrition prediction and house price prediction, and as a result, actually might not be subject to as many of the full scope of concerns as real-world deployment settings. And this can carry implications for ecological validity of studies that I'll discuss later. But a final application of our framework that I'll discuss now is how we can use, how empirical human subject studies researchers can use it to examine these challenges more carefully. And in particular, we extend a recent review of prior empirical human subject studies through the lens of our causal framework. And this is a review that was actually published here at FACT and presented on Monday. We included a scope of studies from 2018 to 2022 in a lot of premier venues, with our main criterion that it includes an experimental human subjects evaluation of algorithm-assisted decision-making. And for this approach, we mapped our primary research question to the relevant subregions of our causal diagram. So for instance, if a study presented a human subject with some explanations and they're looking at the downstream impacts on decision quality, we'd map it to this joint human algorithm decision-making region. A really key result of our work is that 92% of the studies in our review examine a very surprisingly narrow subregion of our causal diagram. Primarily the region that involves human predictions and human decisions and model predictions, model features, and proxy labels. But this work doesn't examine in detail outcome measurement error, treatment effects, and model unobservables. However, we do find that many subregions, while they remain largely unexplored, there's an early yet incomplete view of some of these studies. For example, a couple studies examine human-only features and outcome measurement error, but some regions remain largely or entirely unexplored. Our framework can also be used to improve the ecological validity of online studies, and I would direct you to the supplement of our work, where we break down the experimental design of a lot of prior studies and we map it to our causal diagram. Then we discuss the implications for this mapping for the ecological validity of this study when its findings are then transported to a real-world algorithmic decision support deployment. So I invite you to check out our appendix for a really detailed breakdown and an application of our framework to these different settings. In summary, we develop a framework that helps the FACT community bridge this gap between a lot of the complexities that you're hearing about in some sessions and our current research practices when it comes to experimental human subjects research, And yeah, we invite you to check out our work for additional information, and looking forward to roundtable discussion. Thanks.
Next presentation will be ACROCPOLIS, a descriptive framework for making sense of fairness.
Hi, good afternoon, everybody. My name is Virginia Dignam, and I'm presenting something else. Something else. It's a bit of a mess session. Good. My name is Virginia Dignam. I'm a professor of responsible artificial intelligence at Umeå University in Sweden. And I'm presenting joint work with many of my PhD students and also other colleagues from within the group, but also other ones. The whole idea of the paper starts from a discussion that we had a couple of, like 1.5 years ago, on which we tried to make sense, basically like the title says, make sense of all the different frameworks of fairness that are available, the different ways that people are dealing and defining fairness, using fairness, understanding fairness, interpreting differently the different notions of fairness. So we really tried to start making sense. And to do that, we came up with this framework, ACROCPOLIS, which is an acronym for the different concepts in the framework. And the idea is, of course, like you all understand and are aware of, there are many frameworks or many formal notions of fairness. Most of them or many of them are mutually incompatible. You cannot really translate one into the other. They are just different things, and they all are called fairness, but what they have really to do with each other is quite unclear. And also at the same time is well known that there is a lack of agreement about what type of notion of fairness is more usable in a specific context, what are their strengths and weaknesses, how can we decide in a design perspective which of the different notions of fairness should be used. There is also many technical and formal approaches. All of those have limitations. Some of the limitations are more societal, so many of them fail to address the communities that are disproportionately impacted by the systems being developed. But other ones are more type of technical, and they fail to take into account many of the social technical factors that are relevant to assess fairness. So they only focus on a very limited part of the whole context. At the same time, we are all aware that AI systems are not value neutral, are products that are shaped by and enforce the social, political, and economic structures in which they are developed. So it's important to understand and to be able to deal with the different approaches to fairness that these systems are embedding. So our aims are to contribute to the shared understanding of what fairness means within the AI community, to examine the essential aspects that should be part of any framework that addresses fairness, but also be able to address the systemic factors that need to be considered and that might be otherwise overlooked if we don't really have a common basis to talk about fairness. So, and we also try to provide the means to represent in a more accurate way all the elements and the concepts and the relations between these concepts that should be underlying any fairness framework, and that should be needed to assess the difference between these frameworks. So the background, and this is work that probably is well known for most of you. Fairness is understood and studied differently in different fields. Fairness in philosophy is completely different from what we talk about fairness in AI or data ethics. the traditional operationalizations of fairness are very difficult to adapt to a broader societal concept, are very contextual, are very basic, based in a specific interpretation and a specific system and so on. Fairness, of course, is tied to many of the problems that we see, or the societal problems that we see associated with the use and development of AI, like discrimination, bias, harm, and so on. And also, assessing fairness means that we need to have some means to compare, to basically describe in a uniform way the different bias, what is undesired bias in a specific situation. And also we need to be able to identify and include in the frameworks the different stakeholders, the different context characteristics, and the different types of outcomes that are addressed by the specific system. And also, finally, fairness is a very multidisciplinary, multidimensional concept, and it is just using some quantitative bias definitions or the debiasing methods, statistical debiasing methods, in most cases leads to new bias and to new fairness problems. So Acropolis is basically a set of building blocks, and we tried to, from the different works and fairness and frameworks that have been proposed in literature, we tried to distill the basic concepts that we need to talk about when we want to talk about fairness. And it comes to the acronym Acropolis. So we need firstly to identify who are the actors, who is affected or affecting the processes that we are analyzing, in which context are these processes implemented, or are these processes visible? What are the structural aspects of this context that needs to be taken into account? What are the resources? So what are we counting fairness about? What are the outcomes that we consider to be fair or to be unfair? And for who are those outcomes fair or unfair? Which are the criteria that are influencing this type of outcome? So what are the kind of steps and the structural aspects of the context, or what kind of resources are involved in determining what is fair or what is unfair? And that, of course, depends very much in the different contexts. Which is the power of the different actors to affect or to be influencing the fairness or the outcome of the system? And finally, how can we link these things together? So basically what we have here is a starting proposal for an ontology, which will potentially lead to an analytical tool that enables us to better understand social technical complexity involved in these fairness assessments. With having this and having a basis as kind of the common building blocks will enable also to compare different views on the same issues, and also to compare different definitions of fairness. So putting these building blocks together, we create an initial proposal for an ontology in which we describe the actors as being concepts. All the boxes are concepts in this ontology, which are linked by the arrows, which are the ways that you can relate one concept to another. So actors exist in a specific context. The context and the definition of context will determine which are the resources that we are referring the fairness to. The power is related to actors, but is also a way to modify or to act or to impact the context. The context influence which kind of criteria we are looking about, and the outcome is a way to redistribute or to distribute this type of resources, and also the resources will be linked to the actors, and depending on how the resources are distributed by the actors, it's when we talk about what is fair or what is not fair. So based on this initial ontology, we applied it to a couple of cases. One of them is the infamous Compass case, in which we looked at the way that the different actors have defined or have interpreted how how the fairness, why one says that it's fair and the other one says it's not fair. So it's just an analysis, and I don't have much time to go into detail, but we can see that the kind of issues that are then very easy to evaluate is what are the links that one of the actors is looking at, but the other one is not really seeing as a link. What kind of the context and the power aspects are being identified by one of the actors and not by the other one? What kind of conflicts are there? And for instance, North Point, so the ones who developed the COMPAS system, design it or see that it declare that it is fair because they look at basically that the criteria that have been determined are determining the outcomes, and outcomes they are mirroring the context, the demographic context in which is developed, whereas the ProPublica, the ones who contest or who complain that the system was not fair, see it differently. They see that the context influences the criteria, and by influencing the criteria, the context itself is determining the outcome. So you cannot really just say that you start at the criteria and then the outcomes are aligned with the demographic context, but this demographic context is already determining the outcomes. So they look at it differently, and the model enables to identify this type of difference. We did it again with two different papers which look at fairness and potential lack of fairness of the attribution of and the ranking algorithm of videos in YouTube, which are based in two existing papers. I don't really have time to go into it. And basically the paper ends with a plea for discussion. It's basically what we want is to start a discussion. So far we have used this as an analysis tool, but even as an analysis tool, we would really like to appeal to all of you that are interested in this topic to really look at the concepts, see that apply them to other contexts, to start a discussion. Are these concepts sufficient? Have we identified all the different elements that need to be part of this, this ontology? And finally, how can we use this ontology not only to analyze existing situations, but to start designing situations in which the fairness is better understood and better evaluated. Thank you.
Next presentation will be how biased are your features, computing fairness influence functions with global sensitivity analysis.
Hi, thanks. I'm Vishwamitra Ghosh. I'm a PhD student in National University of Singapore, and this is a joint talk with Devabroto Basu and Kuldeep Mill. So in this presentation, I'll talk about explaining fairness in machine learning. Explainability and fairness are two important research problems in machine learning. While a considerable amount of work has been done in explaining model prediction, there has been less attention in explaining fairness, which we address in this talk. So I'll start with an example scenario where I'll demonstrate the fairness problem. Let us consider a classifier that can be used to predict whether a person is eligible for health insurance or not. And here, the classifier's input are the fitness, income, and age of a person. And we consider age as a sensitive feature, and there are two sensitive groups, elderly and younger. And let us consider the data distribution where the elderly has lower fitness but higher income, and the younger has the opposite feature values. Now consider this decision tree classifier, which makes prediction based on the sensitive feature. So this classifier is unfair, and it is biased towards the younger because they always receive health insurance, whereas the elderly are denied. And now fairness matrix comes into the play where it can quantify the bias of the classifier. For example, one such group-based fairness metric is a statistical parity, which is the difference of the conditional probability of positive prediction of the classifier for the most favored sensitive group to the least favored sensitive group. And in this example, statistical parity is 1, and younger group is the most favored group. Now take this classifier, which doesn't have the sensitive feature in any of the node. But this time, we see that the statistical parity is 0.53. So while in the last example, the sensitive feature was in the root, and it was responsible for bias, in this example, the sensitive feature is, in fact, absent. So it is hard to reason why the value of statistical parity is 0.53. So in other words, what I am trying to say is that there are fairness metrics which can quantify the bias of a classifier with respect to some data set. But it cannot truly explain how the sources of bias. And one way to explain the sources of bias is to decompose bias among different combinations of features. So in this presentation, I'll talk about fairness influence function, which provides a way to decompose the bias of the classifier among different combinations of features. So for the running example, we can compute the influence of the feature fitness on statistical parity as 0.35, and for income it is 0.09, and the combined effect of income and fitness is 0.05. And when we add all these influences together, that approximates the statistical parity of the classifier. And fairness influence function can also witness the impact of affirmative action on the classifier to reduce statistical parity. For example, since we know that the elderly are discriminated, but they have higher income, one way to reduce statistical parity would be to make the threshold on income lower, which is shown in the green node. And now statistical parity has become close to 0, and in the plot of fairness influence function, we now see that income now has a negative influence towards statistical parity, and it can nullify the influences originated from the other features. So formally, we are given a data set which contains both sensitive and non-sensitive features, a binary classifier, a fairness metric, and an integer threshold lambda, which can denote the order of intersectionality, the maximum order of intersectionality. And our objective is to compute the fairness influence for each possible subsets of features GS. Fairness influence function has been studied recently, and the most related to our work is local explainability methods such as SHAP, which applies local explanation to generate this type of influences. And another related work is quantitative input influence, where we compute influence by replacing each feature with some random values and observing how much unfairness shift from the original value due to the replacement. Since our work is related to the feature attribution approaches, we observed the following limitations of the state-of-the-art techniques. One limitation is the less granularity, because the local explainability approaches do not consider the intersectional effects of multiple features on unfairness. And another thing is that group fairness, and particularly statistical parity and this type of fairness definitions, are some hyperproperty of the classifier. Whereas, so applying local explainability to generate explanation for group fairness is only empirically justified, and we see that these approaches are less accurate in approximating bias through the computed influences. So our contribution is a framework called FairExplainer, which can compute fairness influence function of both individual features and intersectional features. And the key idea here is to rely on a literature called global sensitivity analysis. And this is a standard method to assess the quality of numerical models. So we looked into a particular form of sensitivities, such as the variance of a function. So here the key idea is that we want to decompose the variance of a function into the sum of variances of the same function, but for all possible combinations of input variables, and then apply the similar idea for decomposing the bias among different subsets of features. So here, let's take this real-valued function f, which operates on a set of variables g1 through gm. And the idea is that we can decompose the function f among different orthogonal component functions. For example, here f naught is a function which is basically a constant, and fi is another function which only takes gi as input, and fij is another function which takes gi and gj as input, and so on. So basically, in this decomposition, all the component functions on the right-hand side are orthogonal. And since they are orthogonal, now we can take the square integration on both sides, and that basically gives us a way to decompose the variance of a function into the sum of variances with respect to all possible subsets of features. And this is basically called a functional ANOVA, which is widely studied. Now let us come to our fairness context, where we'll apply the similar idea. So the first step would be to review the existing fairness definitions in terms of the variance of prediction. So let us take this statistical parity fairness definition, and here we see that the key function in statistical parity is basically an indicator function, which basically says what is the conditional probability that the prediction is positive for any sensitive group. And we can now think of this indicator function as a Bernoulli random variable for which we know that its variance is its probability multiplied by 1 minus probability. So basically now we can rewrite a statistical parity in terms of this scaled variance differences. And then we can apply variance decomposition and formulate a fairness influence function for each of the decomposed variances with respect to a subset of variables. And it has several implications. For example, now when we apply this decomposition, the cardinality of this subset denotes whether the influence is for an individual feature or for a subset of features. And also the sign of this influences now denotes whether the features are increasing bias or decreasing bias. And we can also devise some properties of this influence function, such as decomposability, which basically says that when we add all the influences together for all possible subsets of features, that should be equal to the bias of the classifier. Now, let's look into this illustration on the COMPAS dataset, where on the left-hand side, I only show individual influences, and on the right-hand side, I show both individual and intersectional influences. And here we see that there are several features which has negligible individual influences, but they can be highly correlated with other features, resulting in higher pairwise influences. So our framework provides a way to now dissect fairness metrics in a higher granular level. And now we also did some study to see what is the efficiency of our approaches in terms of approximating bias through the computed influences. So here in this table, the last 3 columns basically shows the approximation error, where we basically see that in our method, when we plug in to compute pairwise influences, it achieves the lowest approximation error. And we have also published a tool as a Python library, so you can try it out. And with that, I'd like to thank you all.
Our next presentation would be fairness auditing of urban decisions using LP-based data combination.
Hi, everyone. I'm Jing Yi. I'm presenting the joint work with Joe Miller and my advisor, Professor Hennessy. We started our research by looking at the Chicago 311 non-emergency dataset. These types of urban decisions are important because they influence the allocation of resources. By auditing them, we can improve cities' decision-making mechanism. What we want to measure is whether the city is being fair regardless of individual's background. So background information like race or gender are called protected attributes. Usually, they are not available in urban data. We need to rely on other sources to do the auditing. Some examples of these sources, like census, will give us demographic information. and the tax rate or zip code will inform us about individuals' socioeconomic status. We call this data the secondary data. To combine them with the primary data from the city, we use the proxy variable Z, which links two data sources together. Previously, there are lots of discussion on how we should measure the fairness. So one popular choice is the demographic disparity DD. It's the difference of probability of success between group 1 and group 0. Under this definition, there is a next paper by Kellos and others where they give an analytic formula for the upper bound and lower bound of demographic disparity, without making any assumptions on the relations between two data sources. However, in Chicago 301 dataset, what we have is the response time of requests across city blocks. The decision is the response time and is continuous. We can still utilize the demographic disparity by taking threshold of unfold response time t. We now have the demographic disparity measured. We now have the demographic disparity, which is the difference between the CDFs measured at each threshold. The natural extension of demographic disparity from binary to continuous is to consider the supreme distance of our thresholds. So this leads us to the concept of fairness. Leads us to the concept of fairness measured in terms of Kolmogorov-Smirnov distance. This is the definition of demographic disparity that we adopt in our paper, denoted by KSD. So to calculate KSD, we need FT given A, but we never have T and A in the same place. We have the decision T and the proxy variable Z from the primary city data. We also have the proxy and the protected attributes from the secondary data. We can now look at the largest and the smallest this KSD can be over all couplings, which is all FT given A compatible with both sources. That gives us the upper bound of KSD, the KSD plus, and the lower bound of KSD, the KSD minus. The Kellos and others method give us a direct way to tightly compute the upper bound KSD plus, but not the KSD minus. So the main focus of our paper is to find a pragmatic way to compute this lower bound KSD minus. Well, this is the exact expression of KSD minus. When we're dealing with the empirical distribution derived from data, we rewrite it as the following optimization problem. Here, the minimization over X is finding the coupling that gives us the smallest disparity. And the maximization over the threshold J is finding the difference between the CDF. All the intermediate variables are the empirical expression of two data sources. At this point, we observe that in this empirical lower bound, both the objective function and all constraints are convex. So this allows us to rewrite everything into a standard linear programming problem. Furthermore, we managed to represent all matrices in linear programming into sparse matrices, which gives us efficient computation for the experiments. We also showed that with enough data, this empirical lower bound will converge to the theoretical bound. Now the question is, in practice, does our method give any better bounds than Kellos' method? So going back to the original motivation of this paper, we want to study the Chicago 311 non-emergency dataset. So in this dataset, there are lots of request types, such as cut a tree or remove abandoned vehicle. These types of requests have different general processing time, so we study them separately. For each request type, we have a set of TZ pairs representing a request come from block Z, and the time t it took for the city to fulfill this request. We also have the secondary census data, which gives us the demographic distribution within each block. Also, we can choose any demographic splits as we want, such as white versus the rest, or Asian versus African American. Now let's see the results. So let's look at the first column. The images are the plots of analytical results for two different request types and the different demographic splits. In both images, there are two curves and three horizontal lines. The curves are the bounds of Calais method at each threshold. The important result is the three horizontal lines. The red dotted line is the lower bound of Calais method, and the blue line, the blue line is the lower bound of our method, and the blue line is the upper bound of both methods. You can see that our method does provide a tighter lower bound. It is important to have a tight lower bound because it tells us that the city could be pretty unfair even under the most optimistic setting. So to see how often we see the improvement between the lower bound, let's look at the second column. We run the same experiments for other request types. You can see that for two different demographic splits, more than half of the time we see the improvement between the lower bound. The other advantage of our method is that our linear programming will output the coupling Ft given ZA that achieves this lower bound. In this Chicago map, we draw a heat map for demographic disparity for the no water complaint request type. The blocks are colored from green to red in order of increasing disparity. We can see that there are certain amounts of red blocks which have high disparity, even under the best coupling. And as you know that most of the African American citizens in Chicago lived in the south side of Chicago, and most of the white citizens live on the north side of Chicago. So there are more results, more heat map results in our paper, where you can see the similar result. Thank you so much.
Our last presentation is going to be Luke's counterfactual prediction under outcome measurement error. And this paper also won the Best Paper Award. Let's welcome and congrats, Luke.
Thank you so much.
Congratulations.
I appreciate it. Okay, hi everybody. Thanks for sticking with us. I know it's 5 to 6 p.m., so thanks for hanging out for it. This work is counterfactual prediction under outcome measurement error. And this is also joint work with Amanda Costin and my advisors, Ken Holstein and Stephen Wu. In this work, we study a general setting where an organization is introducing a predictive model to improve some decision-making process. So for example here, building off of the example that we talked about previously, let's think about a setting, a medical context, in which a doctor is aiming to enroll some patients in a high-risk medical program to reduce the risk of cardiovascular disease. In the setting in which we enroll someone in this program, we can give them some additional medical resources which might avert some of the poor health outcomes, such as heart attack, that we might be interested in averting. However, under the counterfactual decision or the other decision to screen out, that same patient might experience an adverse health outcome, such as heart attack. And in this setting, a really key challenge is that we only observe the outcome under one of the possible decisions that we can make, screening in or screening out of the program. And this requires us to estimate counterfactual models of risk, which have been explored in prior work. However, another really critical issue that arises in this setting is that often the outcome that we're interested in predicting, such as heart attack, this target outcome, is imperfectly reflected by some proxy, such as heart attack diagnosis and medical records. And again, heart attack outcomes can be imperfectly recorded through diagnoses based on outcome measurement error. So here we can have some measurement error between the target outcome that we're interested in predicting and its observed proxy. But however, we see here that these treatment effects of decisions on outcomes can interact with measurement error in really nuanced and challenging ways. For instance, in a setting in which we screen someone into the program, we might actually have additional physician resources and attention looking at this patient, which means that this patient might have actually had this outcome observed correctly, whereas someone screened out might not have had the same attention and might have a differential measurement error rate. And this interaction between these two can be quite complex. So in this work, we formalize this and we study this general setting of treatment conditional outcome measurement error. And in particular, we offer the two higher level following contributions. First, we show how to learn reliable models under this setting of treatment conditional outcome measurement error. And secondly, and more broadly, we underscore the importance of really carefully addressing these intersectional threats to model reliability while developing these predictive models for decision support. So now let's talk about setting up our setting in a little bit more detail. In this case, we're interested in predicting the risk of some unobserved outcome of interest, such as heart attack, which is this target potential outcome. There we go, 1 second. Yes, but instead of observing this target outcome directly, model developers and different stakeholders actually have access to some of this observational data that's going to contain covariates, prior decisions, such as physician decisions, and observed downstream proxies. And in this case, it's really difficult because we can't estimate the target outcome of interest given our available model development data. But in this work, we model the relationship between the target and proxy outcome via this treatment conditional outcome measurement error model, in which we assume that there's this treatment conditional false negative and false positive rate, but that this measurement error remains fixed across covariates. We'll also require some standard causal identification assumptions for the approaches that I'll talk to you about today. What we'd like to do in this setting, and following the really common setup of what we do when we're developing predictive models for decision support, is we'd like to minimize the expected risk with respect to these target potential outcomes for some prediction function f sub t and some loss function. However, the really challenging thing here is that we don't actually have access to these target potential outcomes available in our model development data. So what we do in this work is we develop an alternative to this that can be actually used to estimate the quantity of interest given observational data, which we call the reweighted surrogate risk. And this reweighted surrogate risk simply combines a reweighting function with a surrogate loss, and we minimize this over the treatment population that we're trying to estimate risk for. What's really beneficial about this setup is that we can actually minimize this risk over our observational data that we have access to in our historical model development data sets. In our work, we provide the following result, which shows that the expected risk with respect to target potential outcomes is equivalent to the reweighted surrogate risk that we minimize over observational data. So these two risks are equivalent. And intuitively, you can view this as applying a joint bias correction for treatment effects, outcome measurement error, and selection bias in parallel. However, an important nuance of this is that this result right here requires knowledge of our measurement error parameters to construct a surrogate loss and our propensity scores to construct a reweighting model. And this motivates our practical finite sample algorithm, which can be estimated by learning our reweightings and our measurement parameters and then minimizing this over a treatment population T. And I invite you to take a look at our paper for some details on this approach. But at this point, you guys might be wondering, in this setting, we don't often have access to the measurement error parameters of interest. And in fact, these parameters alpha and beta might be unknown because we don't actually know the relationship between the thing that we're trying to predict and what we actually have available in data. So it's really challenging to somehow reason about this difference between what stakeholders are interested in and what we actually have available in our data sets. So we propose a flexible set of anchor assumptions. And these anchor assumptions provide multiple different options or combinations of assumptions that can be flexibly combined to recover estimators for target potential outcomes of interest. So I'll introduce these in the context of identifying the outcome of some disease of interest. So here, this min anchor assumption assumes that there's some patient in our population that has has no risk of this outcome of interest. So for example, we can verify this, and this could be reasonable if we have, based on some detailed knowledge of patient physiology, we know that this disease isn't present for at least one patient in the population. And this base rate anchor assumption assumes that we know the target potential outcome class probability assumes some scalar value t. And similarly, this max anchor assumption holds that there's someone in the population that has guaranteed risk of this outcome, which can be verified by some confirmatory tests or some gold standard diagnostic tests based on what's available in medical records. So I won't go into the details of these assumptions, but the important takeaway from this is that we show how you can combine these different assumptions to recover an estimate of the measurement error parameters in a flexible way, depending on which assumptions are reasonable in a specific deployment context. So while one or more of these might not be reasonable in a specific setting, you can really pick and choose which ones you'd like and recover measurement error parameters flexibly. And again, we invite you to check out the work for some detailed algorithms and proofs for this result. An additional challenge that arises in this setting is that we have really compounding uncertainty from unobserved counterfactuals and outcome measurement error, which poses a really critical evaluation challenge. So we start by verifying our approaches with a synthetic evaluation in which we have a lot of control over the data generating process. And in this plot that I'm showing you here, I'm not going to go through the setup of our synthetic evaluation, but what you can see here is that we're comparing a couple different methods across different sample sizes. And this model here at the top is an upper bound on how well you can do in this task, assuming that you know those target potential outcomes, y star sub t that I talked about earlier, highlighted in yellow. So if you know those exactly, this is how well you can do. And this next plot here, this reweighted surrogate risk, our approach, performs reliably across different measurement error parameter settings. But we see that its performance breaks down when our measurement error parameters are estimated, as shown in those dashed lines. We also run an ablation without reweighting. But the important thing that I'd like to focus on here is what happens when you don't correct for both outcome measurement error and treatment effects in parallel. What you see is that across all of these different settings, different sample size settings, models perform quite unreliably. And this really underscores the need to carefully consider both of these challenges, which we know impact predictive models in a lot of real-world algorithmic decision support settings across education, healthcare, lending, et cetera. So to kind of build on this point a little bit more, we can conduct an additional evaluation with semi-synthetic data. So we look at a couple different prediction tasks using randomized controlled data from randomized controlled trials in the healthcare and employment domains. So in this first evaluation, we're predicting diagnosis with a new active chronic medical condition, given enrollment in Medicare, or in particular, an opportunity to enroll in Medicare based on a randomized lottery. And in addition to this, we also have this jobs data set in which we're predicting downstream unemployment, given an opportunity to enroll in a employment retraining program. And this data set has a randomized and non-randomized component that's pretty convenient for evaluation. What we do with these data sets is we insert some synthetic selection bias in the randomized component for the training data, and then we also insert some synthetic outcome measurement error by flipping these measurement error parameters, alpha and beta, with a known probability. And here in this evaluation, I'll show the results of these approaches. So similarly, here we're plotting the bias and average treatment effect estimates across a couple different measurement error parameter settings. And we see a similar story here. In particular, models that don't correct for outcome measurement error and treatment effects in parallel perform quite unreliably across model settings. However, our reweighted surrogate risk proposed approach performs comparably to this Oracle model, the CT model, which again has access to the idealized amount of information that's available in this setting. But this panel here on the left shows a setting in which we know the measurement error parameters because we introduced it artificially. And we're using those measurement error parameters during risk minimization. But you might wonder what happens when we don't know these in advance. In this panel here on the right, we show the performance of our approach when we leverage those anchor assumptions I just told you about for error parameter estimation and then downstream risk minimization. And what this plot shows is that when these anchor assumptions are violated, so in this case the max anchor assumption is violated on both these data sets, our approaches perform quite poorly when we use these estimates for downstream risk minimization. But in this case, when our base rate anchor holds, as it does here in the center, our approaches perform much more reliably. And this really underscores the importance as practitioners and for different stakeholders to really carefully vet these measurement assumptions in consultation with domain experts when we're applying these assumptions for downstream parameter estimation and risk minimization. So that concludes today's talk, and I want to thank you for your time and attention and looking forward to panel discussion.
Let's open the floor for the Q&A session. Let's have all the speakers come back on stage. And if you have any question, feel free to go up to the mic over here. Just ask.
Hi, I have a question, the first presentation. I'm from the Columbia University. Thank you for the great talk. I understand that you focus on the proxy labels in human algorithm decision making. I have some question about the causal graph you use. One advantage of using causal graph, you can explicitly draw the measured variable and as well as the measured variable. But in your causal graph, do you assume that all human-related variables are measured? I was just wondering whether you distinguish measured covariates from unmeasured covariate. And second, in your causal graph, it seems human-related features are considered as a confounder. But in reality, there are different types of covariates, like a mediator or a collider. So, of course, their impacts are different. I was wondering whether you distinguish those different types of covariates and also discuss their impacts in your paper or any future thoughts on your direction.
Yeah, thanks so much for your question. Yeah, it's complex when you try to abstract a causal graph across a lot of different settings. So here we're thinking about education, healthcare, employment. So we kind of glossed over a couple of details that you might be interested in, and we didn't have time in the discussion to get into detail. But to answer your question, we do distinguish between measured and unmeasured variables, and indeed that's really important for the proxy. So you never observe the thing that you're interested in estimating, so that's unmeasured. But the thing that you do have access to is this proxy, so that is measured. And maybe it might have got lost on the talk, we kind of show this in solid lines for the measured things and dash for the unmeasured. So we do distinguish between these. To your point about confounding and mediators, et cetera, maybe we could talk a little bit offline, but this graph does reflect confounding and mediators in a lot of different rich causal structures that can crop up in these settings. And it's kind of abstracted away by the key variables that we show here, which is to really focus on these measurement and target variable related issues. So hopefully that's satisfactory. I'm happy to chat offline too if you're curious in more detail, but keep time for everyone too.
My name is Hari. I'm from University of Illinois. Thank you all for wonderful presentations. And my question is for the last presentation. I was thinking about your notion of the anchor, and you have this idea that the anchor is given. I'm assuming that some expert gives this. But I was wondering, have you thought of maybe extending it, not to have it to be a number, but to have like a prior? And what might, because your results are like, what if you know this and what if you don't know this? But in reality, there could be a prior over that risk, over that anchor value.
Yeah, that's an excellent question. The reason why we kind of, in this work, we specify these as kind of these binary things that either hold or don't hold, and you pick one or you don't pick one. And it turns out if you're wrong, it matters a lot, as we showed in the results. Our specific choice of this is kind of an artifact of the AIR model that we adopted in this work. So we're inheriting kind of a lot of work from supervised label noise work that we kind of adopted this model. And it turns out that that's the easiest way to think about it in this setting. But to your point, I completely agree. I think there's a rich set of ways in which we can think about how to specify this from this kind of incorporating this expert knowledge into thinking about measurement assumptions. I think this is a really rich area for future work that we're thinking about some on our end as well. Mm-hmm.
Hello, my name is Hong Kai. I'm from University of Chicago. I have a question for the second presenter. So in your presentation, you mentioned that the quantitative definition of bias and deep bias will lead to new biases. I feel like it's a little bit counterintuitive to me because like if we cannot define bias, we cannot address it. So could you please like be more specific or like provide some examples like under what circumstances they will lead to new biases? And probably more importantly, how does your framework, the Acropolis, can prevent the invention of new biases in those circumstances?
Yeah.
Thank you.
Thank you very much for your question. Indeed, what we mean is that before we are going to define mathematical or statistical interpretations or ways to address bias, we do need to look at it from a societal perspective and look at all the different aspects and societal impact of the supposed or assumed bias, and if we miss that step, then it's when changing from one statistical interpretation of bias to another one might just move bias somewhere else, because we are missing the link between the societal and the impact aspects and those of what is being interpreted in the statistical or the mathematical definitions of bias. And the way our framework can support that is exactly by providing a structured way to address the social technical aspects in which the system is going to be developed and interpreted. And in that way, you can kind of link the different interpretations or the different mathematical expressions of bias and ground them in societal concepts. Thank you.
Hi, thanks for the nice presentations. My name is Harvineet from NYU. My question is for Vishwamitra. So you touched a bit on how the decomposition from your fairness influence functions can help in mitigation efforts, like how to change the predictor so that it is more fair, or which features to use. So you talked about the example on setting a lower threshold on the income for the older group. So I was just wondering if you can elaborate, like how to go from the decomposition to the mitigation effort.
So I think like that could possibly be done because, for example, people have tried to look into the influences of data points on fairness, and then they apply to kind of reweigh the data points in a way that basically the bias mitigation can be done. So I think similar idea could possibly be done on the feature level, because here we compute influences on the feature level, not on the data level. So I think it's like a future work that one could look into. Thanks.
Hi, I have a question for the third speaker as well. Your work on looking at all the different intersections, I thought that was really interesting. Do you find that there is a theoretical limit as you start to get a lot of different features, with how many intersections you can look at? And how do you approach prioritizing which intersections to look at?
So basically, like in our implementation, we kind of go in the higher order of
Okay, the time is up. Feel free to leave if you have anything else follows. But if you have questions, feel free to ask. I think the speakers will stick around for a while. Thank you all for joining us today.